This is the video for problem 230 of Engineering 623. This problem says, consider a non-reciprocal transmission line having different propagation constants, beta plus and beta minus, for propagation in the forward and reverse directions, with corresponding characteristic impedances Z0 plus and Z0 minus. An example of such a line could be a microstrip transmission line on a magnetized ferrite substrate. If the line is terminated with an impedance ZL and is of length L, derive expressions for the reflection coefficient and impedance seen at the input of the line. So let's look and see how this problem would go. The voltage along the line would consist, as usual, of a forward traveling wave and a negative traveling wave. But now that forward traveling wave has propagation constant beta plus, and the negative traveling wave has propagation constant beta minus. Similarly, the current will consist of I plus of Z and I minus of Z, and the current associated with the forward traveling wave will be the voltage associated with the forward traveling wave divided by the characteristic impedance associated with that forward traveling wave, which is Z0 plus in this case, and then the current associated with the negative traveling wave is the voltage associated with the negative traveling wave is minus the voltage associated with the negative traveling wave divided by the characteristic impedance associated with the negative traveling wave. So that's how we get this expression for I of Z. For V of Z, as usual, we can factor out this first term, and then we're left in parentheses with 1 plus gamma of 0 e to the j beta plus beta minus Z. You remember in the usual case, we would have 1 plus gamma of 0 e to the j 2 beta Z, but now the 2 beta breaks up into beta plus beta minus. And here gamma of 0, as usual, is just V minus divided by V plus. We see that gamma of Z, which is V minus of Z over V plus of Z, is just gamma of 0 e to the j beta plus beta minus of Z. And this is, again, for the usual problem, this beta plus beta minus would just be 2 beta. And we get then the traditional formula. Now, to identify what gamma of 0, remember that gamma of 0 is V minus over V plus, but to get some more information about that and be able to actually solve for it, we can begin by noting that the load impedance CL is V of 0 divided by I of 0. And so if we look at our formulas up here for V of Z and I of Z and evaluate them at 0, we get ZL is equal to this quantity, which then can be written as this. And so if we do a little bit of algebra on that, it looks like this, and then cross multiply and rearrange terms, and we end up with this, which is very familiar looking. It looks similar to our usual reflection coefficient at the load, but there are differences. Remember, the traditional formula for the reflection coefficient at the load would be ZL minus C0 over ZL plus C0. But now that we have different Z0s, this will become ZL minus times ZL minus Z0 plus divided by Z0 plus times ZL plus ZL minus. So, and of course, you can see that if Z0 minus were equal to Z0 plus, then this would reduce to the usual formula. So definitely for this problem, you should have been able to get to this point. You should have been able to derive this formula for gamma of 0. And in fact, since gamma of z is simply equal to gamma of 0 times e to the j beta plus beta minus z, you should be able to get this as well. And so if we wanted the gamma at the input of the line, we just substitute z by negative L, and we would have gamma at the input to the line. So this much is, I think, easy to get. But now when we want to get z, that begins to get a little more complicated algebraically, and I'll just show you what I did, but I wouldn't worry too much. It's as was the case in problem 2.25, is sometimes not exactly clear where to terminate these calculations. So you may arrive at a different answer from me. But anyway, z of z is equal to v of z over I of z, and so we substitute our expressions for v of z and I of z. And then we begin just doing some algebra to try to simplify this, and ended up getting this expression for z of z. And notice that this would get quite complicated. There would be quite a bit of work to do if we went ahead and substituted for gamma of z, but what I decided to do was just to leave it as this. So when we evaluate these expressions for z of z and gamma of z at negative L, we get z of negative L, which is one of the things requested for this problem, is z0 plus z0 minus times 1 plus gamma of negative L over z0 minus plus z0 plus times gamma of negative L, where gamma of negative L is equal to this expression right here. But I would not expect you at this point to go ahead and make the substitution and try to completely simplify this, because that would be quite a bit of work, and I don't think that that's really the point of this kind of problem. So the main thing, once again, you should get this expression for gamma of 0, this expression for gamma of z. Both of those for sure you should have been able to derive, and I think that's the main point of this problem. So that concludes problem 230 for engineering 623.